welcome back. It's great to see everybody. Thanks for joining us for a great talk by Dobie. Dobie, it's wonderful to see you again. Welcome back to Berkeley. Even though very few of us are actually there, I guess. Most of us are around the world now, but it's great to see you back. Dobie, as most of you know, or most of you may know, was a postdoc in Berkeley a few years ago. Since 2015, he's been a professor at Georgia Tech. He was a postdoc for a couple of years in Berkeley, and before that he was a grad student at Columbia, and he did his undergrad work at Harvard in psychology. Wow. So you may know some of the faces here from that time. So Dobie's become very famous for his work on metacognition, among other things. I think he's going to talk about metacognition today, which is wonderful. Dobie, it's a great pleasure to see you again. Thank you for joining us and giving this talk.
Thank you. And it's a great pleasure. I had a wonderful time at Berkeley. It was from 2012 to 2015. So that was 5 years ago now. I was in Mark Desposito's lab, which at the time, and I don't know if that's the case right now, was sort of off in a different building. So that was a little unfortunate actually, because I think I saw many of you only at talks, but like not in the hallways and all of that. Can you see my screen okay? Yes. It's okay, it's slightly different view than before. Oh, let me start the, okay. And I will change things here a little bit. Okay. All right. So as Christina was saying, feel free to interrupt me throughout. You know, just jump in if you have any questions. So I've been at Georgia Tech for the last 5 years, and what my lab studies, I'll be talking about metacognition today, but what my lab really studies is perceptual decision making. Perceptual decision-making is a big term and not really well defined yet, but what we mean by perceptual decision-making generally is the process of deciding what is out there in the world. So if you see any kind of random picture that I got from the web, and I ask you about any object in this picture, as long as it's ambiguous, as long as you know there's any kind of decision to be made about it, you're engaging in a process of perceptual decision making. So in my lab, we're interested in pretty much all aspects of perceptual decision making, and in order to study that, we try to figure out what are the different components, and then try to understand each of those components. So what are the components of perceptual decision making? We think that it's actually relatively simple. You start with some sort of a stimulus in the environment. That stimulus leads to some sort of an internal representation, right? You represent internally the stimulus. Based on this internal representation, you make a decision about the stimulus. And finally, once you make a decision, you evaluate that decision. So it's really a several step process. And in my lab, we're interested in all of them. So let me quickly tell you about some of the stages that I won't actually have time to talk about today. First, the stimulus. So that's the simplest part. So the kind of stimuli that we use in the lab, we are good psychophysicists, so we use Gabor patches and random dot motion, and usually we use two choice tasks. You know, is it counterclockwise or clockwise? Is it left or right motion? But more recently, we started to use multi-alternative tasks. So this is from a recent paper of ours where people can, in different conditions, choose between 4 alternatives, or we give them 2 alternatives. And actually it turns out that these kind of manipulations where you give people more than 2 alternatives are full of surprises. So I anticipate this is going to be a major part of my lab going forward, but I don't really have time to talk to you about that today. So the stimuli are not the interesting part. The interesting parts are the next parts. So the internal representation is one thing that we are very, very much interested in, but you know, I won't have time talk too much about it today. So I just want to give you a flavor of the kind of things we do in the lab. So the big question here is, how is information represented internally? And weirdly, and you know, I'm talking to a bunch of vision scientists, you probably know that we actually understand much less about that than we should, given that we've been thinking about these things for a long time. And there's a number of questions here. One really fundamental question is the representation probabilistic or not? So what is a probabilistic representation? A probabilistic representation is a representation where different world states are represented probabilistically. So if I get something from my desk and I show you this, can you see it? Can you see my video?
No.
Yes, no?
No.
Oh no, you can't see my video. All right, well, I was showing you some random
we can
object.
see it. I think some of us could see it because I could see a lot of people nodding.
Oh, okay, all right, right. So anyway, if I just show you a particular object that has a particular color, so for those of you who can see it, you can guess what the color is, but there's a question of like, do you have a probabilistic representation over the possible colors? So this particular color is something that is yellowish, greenish. And the question here is, do you have a representation where you represent yellow with some probability and green with some probability and yellowish, greenish with high probability? Or do you just guess that it's yellowish, greenish and that's your guess and you just have some sort of uncertainty about that? So I have written some theoretical pieces, and we recently published an empirical piece that actually argues that our representations are not probabilistic. So we're taking a very controversial stance on this issue, I guess. Another line of research is the drift diffusion model. So we're interested in these ideas of accumulation to bound when modeling reaction time. And again, we have written some theoretical pieces, and we have some recent empirical work that is not yet published that suggests that there's strong limitations on these ideas of accumulation to bound, and we're actively working on building competing models. Finally, in a few recent papers, we have been thinking about perceptual learning and how newly learned information is represented internally, and what we find is that after you learn during periods of restful wakefulness, so when you're not doing anything but you're just lying in the scanner, we can see that the same stimuli that you were just learning are reactivated in V1. So this is called awake reactivation. This is a phenomenon that has been found in the hippocampus a lot, and in some high-level cortex, like the prefrontal cortex and parietal cortex, but it wasn't clear that it happens as early as V1. So, so we've been working on that. So these are some areas where we're working on in terms of the internal representation. Then once we understand, what is the internal representation, we need to make a decision on top of that. So again, there's a number of issues here that one can be interested in. What we try to study are a few questions. One is, how good are our decisions? So together with Rachel Dennison, who was also at UC Berkeley, she was a graduate student there a bunch of years ago when I was also a postdoc there. We have published an article that argues that suboptimality in perceptual decision-making is the norm rather than the exception. So that was an article that received a bunch of commentaries, and we responded, and it was quite controversial again. But in less controversial areas, we have been looking at what are the different biases in decision-making, as well as how is decision-making modulated by things like expectation and reward, by attention, and by cognitive control. So lots of stuff there. If you want to know more about any of these, you're gonna need to invite me again. But right now for today, I'm gonna focus on that last stage, which is evaluating the decision that you just made. So evaluation is the idea that you have made the decision already, and then you're going to a process of evaluation, which we call a metacognitive process, because it's a second level process that looks down at the first level process that made the decision. So this metacognitive evaluation faces several different challenges. One is we need to measure people's ability at metacognitive evaluation. Second is we need to be able to model how people engage in metacognitive evaluation. And third is we want to understand how the brain does metacognitive evaluation. What brain areas are important? What is the mechanism? So each of these three areas we have done quite a bit as a field. We have about a half dozen measures of metacognition. We have maybe a dozen different models of metacognition, and we have maybe a couple dozen papers on the neuromechanisms of metacognition. And yet, if you look at this literature closely, you can discover something that is sort of disturbing, and once you appreciate it, you realize there's an issue there. The first issue is that the measures of metacognition that we have and the models of metacognition that we have, they are pretty much independent of each other. So there's this important relationship, which is that a measure of anything implies a model of that same thing. And conversely, a model of something implies the correct way to measure that same thing. So given that we have these measures, all of these measures, and we have all of these models, you would expect that there would be a clear relationship between them. But in fact, those have been developed completely independently, and there's absolutely no crosstalk. Similarly, you would want your models of metacognition to be linked to your understanding of what the different brain areas are doing, but those two things are largely independent as well in the literature. So in the last few years, we have been working on building connections between these. And what I'm going to tell you about today are three things. First, we're going to develop and test a model of metacognition. We're going to then use that model to derive a measure of metacognition that is theoretically inspired, and we're going to be now able to link the measure with the model. And then we're going to also use the model in order to understand in a more computational way what are the different brain areas that we know are involved, what are they actually doing in terms of computation. So this is the plan for today. Does that make sense to everybody? I guess this is not really an interactive kind of a environment, but all right. So let's go forward. So we're going to start with developing and testing a model of metacognition. Okay, so what do we want from a model of metacognition? We want it to explain the most important observations that we see in the data. And by far the most important observation is that metacognition is imperfect. What does it mean that metacognition is imperfect? Well, so I'm sure, are all familiar with the concept of D prime. So this is stimulus sensitivity in a two-choice task computed from choice data. So D prime quantifies our sensitivity to the stimuli. Now, similarly, we can derive this other measure called meta D prime, which is the same sensitivity, but computed from confidence ratings. So we call this metacognitive sensitivity as opposed to stimulus sensitivity. Now, the good thing about meta D prime is that it is in the same units of D prime, so we can directly compare the two measures. So the standard way of doing that is to take their ratio, and if we take the ratio, we get a new measure called M ratio, which is meta D prime divided by D prime. And empirically, we know that this measure is usually less than 1. So what that means is that metacognitive sensitivity is usually lower than the stimulus sensitivity, which is evidence for the existence of metacognitive inefficiency. So metacognition is imperfect, it's inefficient, and we know that empirically from these findings that M ratio is less than 1. That makes sense? Okay. So how do we model this metacognitive inefficiency? The simplest way one can think about that is to introduce a noise term that is specific to the metacognitive ratings, and we call that metacognitive noise. So more formally, metacognitive noise is noise that affects the confidence ratings, but not the decision. All right, so the metacognitive ratings are going to have this extra level of noise. So how would a model look like that incorporates metacognitive noise? So we can start at the stimulus level. Again, we're looking at a 2-choice task. So for example, we can say that the task is distinguishing between a left-tilted Gabor and a right-tilted Gabor patch. So at the stimulus level, these are stick functions, so they're fully distinguishable. This S1 is stimulus 1 and S2 is stimulus 2. Now, of course, there's noise. So we have these stick functions are going to be corrupted by sensory noise. So this is sigma sensory. And at the decision level, we are going to get these 2 normal distributions, which we can distinguish by setting a criterion somewhere. And this is the representation at this decision level, which is just a normal distribution with mean of mu. So each of these has a mean of mu1 and mu2, let's say, and variance that is sigma sense to sigma sense squared. So this is just standard signal detection theory so far, and this doesn't incorporate metacognitive noise. Now, incorporating metacognitive noise means that there's going to be one more stage of noise corruption where sigma meta, which is metacognitive noise, affects the signal here. And at the meta level, where we give confidence ratings, we're going to have a signal that is noisier. So the means are going to be the same, but now these normal distributions here are going to have higher variability. And assuming that these 2 levels of noise are completely independent, then they just sum up and we get a representation at the metacognitive level that is just noisier, right? These normal distributions have the same means, but they have higher standard deviations. So this is one conceptualization of this. It's meta noise or metacognitive noise added to the signal. Alternatively, you can think of the same model, but where metacognitive noise is added to the criteria. Now, how would that look? It would look very similar. So after the decision level is the same thing, except that now the confidence criteria are not going to be stationary like they're here, but the confidence criteria themselves are going to come from a normal distribution themselves. And that normal distribution is going to have variance of sigma meta squared, which is the same noise as here.
Question.
Go ahead.
You've gone from 1 criterion to 2 criteria, or unless those are the means. So what's going on with those 2 lines, 2 vertical lines?
Yeah, great question. So this is the decision criterion here. Whereas at the meta level, we have confidence criteria. So these are meant to represent the confidence criteria. I should have mentioned this. So
why are there 2?
So there are 2 because this region is going to be high confidence for S1. This region is going to be high confidence for S2. And then here you're going to have 2 regions that are low confidence for S1 this region up to the decision criterion, and this region here up to the decision criterion is going to be low confidence for S2. So because
well, that's a graded scale. The level of confidence.
I'm not sure what you mean. So this would be for a confidence for a.
Well, when you do a
If you only
confidence
have
rate,
low
there's
and
no-
high confidence, then you just set a single criterion. If you have more confidence levels, then you'd need to set more criteria in the signal detection theory framework.
So you have 3 levels of confidence, 0, 1, and 2.
Well, in this case, there will be just 2 levels, low and high.
But they're separate for the 2 stimuli.
They're separate for the 2 stimuli. According to signal detection theory, in this framework, the criteria that separate low from high confidence would be separate for the 2 stimuli. They oftentimes assume to be symmetrical, and oftentimes you would actually fit one set of parameters. But honestly, empirically, they're not. Often the times they're not symmetrical, so it actually makes sense to think of them as 2 sets of criteria on each side,
But
or for each stimulus.
I thought the decision was whether it was one stimulus or the other stimulus.
Mm-hmm. Yeah, so the decision is one stimulus or the other stimulus, but once you make the decision, and then you need to make a confidence rating.
And you're expressing confidence in that decision?
Yes.
Well, where are the 2? What are the 2 criteria then?
So okay.
Can I ask a related question?
Please.
If you just did an experiment with a 4 alternative forced choice where the 4 responses were, I'm sure it's S1, I think it's maybe S1, I'm sure it's S2, I think it's maybe S2, then I would think you would just draw that as a decision level with 3 different criterion boundaries separating the 4 responses.
I totally agree. I totally agree with Jeff, and that you get more information by giving the confidence rating, so the D prime should get stronger. That's the way we've always done these 4 alternative forced choice, 4 alternative decision making.
Well, I'm trying to understand if there's any difference between doing it that way and having the confidence as a separate response and a separate set of distributions.
Correct.
Yeah, so it's an empirical question, but people have actually studied that, and usually the finding is that there's very little difference whether confidence is collected with a separate button press or with the original button press. So whether you say there's 4 options to begin with, or 2 options give a decision, then give me a high or low rating, all of the findings tend to be pretty much the same. So and within a signal detection framework, they'll be modeled the same way.
I thought that metacognition, and am I getting this right? You make a decision, then after you make the decision, you're asked to make a secondary judgment of how confident are you in the decision. So it's not like necessarily, people use rating scales and get proper D primes and they look like the same score. But you're talking about a secondary measure that comes after the fact. Is that right?
Sounds right to me.
Metacognition?
So whether or not you get, whether or not the metacognitive decision comes after or at the same time as the decision is really not critical in terms of the modeling. It doesn't change anything. But yeah, I would talk about what happens when we quantify separately the decision and the confidence ratings, but yeah, I think there's several different questions here. So did that answer about the simultaneous versus 2-stage?
I mean, it doesn't seem to me meta, just as he said. It's not meta unless it's a decision about your decision.
So that's an interesting point. So there's two ways of taking this. One is to just say, well, it's a terminological issue, and maybe the computation is exactly the same inside. But another way of thinking about this is, what is it that metacognition is really? Is it a second system, or is it the same system that makes the decision that just makes a slightly different decision? And I think that's an open question, and this is a big question that I'm not going to go into. But either way you think about it, it's not. I mean, my talk is going to be valid regardless of how you think about metacognition. Usually people think of it as a second system, and that's how I'm going to talk about it, but it doesn't have to be that way.
I have a question. It's really simple. Is my voice on?
Mm-hmm.
And Jeff talked about an experiment where you have 4 alternatives: leftward tilting, I think rightward tilting, I'm sure rightward tilting, okay? Mm-hmm. And when you said metacognition, when you calculate D prime in the metacognition way, which is you build up the ROC, I assume, you have less efficiency, so you would get a smaller D prime. Is that correct? No, I've gotten it wrong. Okay.
Yeah, so I didn't really go into the detail there. So D prime is D prime. So D prime you compute by just ignoring the confidence ratings and just taking the decision and computing D prime in the normal way. Yeah. Meta D prime, it's actually you actually only consider the confidence ratings. So it's not an ROC curve. It's a slightly different technique. But the point is, what is the stimulus sensitivity from the confidence ratings? And when you compute that, it turns out that you get lower stimulus sensitivity. So the confidence ratings carry less information than the decision criterion.
But traditionally, when signal detection was invented, they used confidence ratings to get D primes, and that was considered a useful measure.
That is correct. That is a useful measure.
You're saying that measure is less, you get a lower D prime that way? Is that what you're saying?
That's what I'm saying. Yeah.
Well, excuse me. Isn't it classic that if you've got noise in your criterion, D prime goes down? That's just it's like another noise.
That's exactly this model.
If you can't keep a constant, and if you have multiple places, multiple possibilities, maybe what you're saying is it adds more noise because all the criteria for of the levels of criteria are varying. But this is not something new, I thought, to the detection literature. It's noisy criteria, lower performance.
Yes. So the idea of metacognitive noise, of just noisy criteria, criterion jitter, the same idea has come in many different ways. So this is not something that we invented. This has been there for like many decades.
I see. So you're not adding something sequential, even though you told the story here as though it was sequential, decision level and meta level. You're just talking about sources of variance.
I'm talking about source of variance. So this is one way of thinking about it in terms of like how it's happening, but in terms of the model, it can be sequential, it can be not sequential. It's the same thing.
But it could happen from other things. If the person doesn't keep their criterion constant because they've got a varying notions of costs and values, for example, or of a priori probabilities. If you've got any uncertainty in those variables, and a person includes that uncertainty, they can't avoid it. Well, this is what you would get. Is that what you're saying?
Yeah. So as long as the uncertainty changes from trial to trial, so the same criterion moves around, yes, that would be criterion noise. That would be criterion jitter. That would lead to if it's specific to the confidence ratings, then that would be metacognitive noise. If it is specific to the decision, that would be decision noise.
It's a result of sloppy decision making.
It's a result of sloppy decision making. That's one way of putting it. I think there's it can be the result of things that are not sloppy in the sense that they evolved for a good reason. But when those things are not considered, it looks like sloppy decision making. So for example, there's very good evidence that confidence ratings are autocorrelated. So the confidence rating on the previous trial affects the confidence rating on the current trial. So when you don't account for this, this is going to look like criterion noise, or what I call here metacognitive noise. And you can think of this as sloppy decision making, but there's also good reasons why that we can think of why it evolved that way.
If nothing else, feedback. If you make a decision, you make a decision that you were quite confident in, and the feedback in the experiment, you didn't have the accident or whatever, tells you were wrong, you can imagine shifting your response criterion from trial to trial.
That's exactly what I was going to say.
Yeah. I mean, I agree
minds
with all
think
of that.
alike, Stan.
So I think I just have to be clear. This is not something that I'm saying, we came up with this, right? This is just, I'm just explaining how metacognitive noise would work in a model. I'm not saying this is new or that we invented it. I'm just trying to make it
I understand. Yeah, sure.
clear. All good? All right. So, so let me go on then. So now this model, I'm gonna take the interpretation where the metacognitive noise is added to the signal, but it again is the same thing mathematically. Actually leads to a non-trivial prediction that has not really been appreciated before. And what is the prediction? So we can, from here we can compute the two different things. We can compute d prime, which is just the difference between the two means divided by the standard deviation. So this is again just in standard signal detection theory. And then we can do the same thing at the metacognitive level. So at the metacognitive level, we're going to have the same two means, mu1 and mu2. And then we're going to have the standard deviation is now the square root of the variance here, right? Now, if we're to divide these two things, meta d prime divided by d prime in order to get our measure of metacognition, M ratio, we, the numerators cancel and we get this expression, which is the sensory noise in the numerator divided by the square root of the sum of the two noises. Now, the important thing about this expression is that it's an increasing function of the sensory noise. So, so as the sensory noise, so, if we fix the meta noise to a certain level, as the sensory noise increases, the numerator is going to increase faster than the denominator. So I can plot this for a few different values. So this is sigma meta of 0, then this is just going to cancel out and it's going to be just 1. So that's not going to increase. But as long as sigma meta is a positive number, then as sigma sense increases here on the x-axis, this M ratio on the y-axis is going to increase, right? Okay, so that leads to a very simple prediction of this, which is that decreasing the sensory noise would decrease the metacognitive efficiency M ratio. So if you can find a way to manipulate directly the sensory noise, then what we should see is a movement of metacognitive efficiency M ratio in the same direction. Okay, so again, we start with a model that is not new. This is a model that people have been using, but it's not, but it's always been used as a convenience to fit data, and not as like a model that we are actually going to propose as a real thing in the world that we can then make predictions. And now we're treating it as a real model that is going to make predictions. And it's making this prediction that, at least on the face of it, seems pretty counterintuitive. So we think that decreasing sensory noise is a good thing. So it should increase, difference should increase everything. It should increase metacognitive efficiency. but actually the projection here is that it would decrease metacognitive efficiency, and it comes directly from the model, right? Okay, so how do we test this? We need a way to manipulate sensory noise. So this is, we thought this would be easy, and it turns out it's actually really difficult. So we can easily manipulate stimulus noise, but how the stimulus noise relates to the sensory noise on the internal representation is actually a tricky thing. So what we did is use a couple of different manipulations that are mostly based on learning. So the idea is high noise means that there's more variability in the internal representation. So the trials are more dissimilar. So a noisy internal representation in terms of signal detection theory means that on one trial I get you know, a lot of signal, and on the next trial I get much less signal, and it's just noisy like this. So on the other hand, low noise would be the trials are more similar, more consistent. So the way we're going to manipulate that is through perceptual learning. If people engage in perceptual learning, then they should get more consistent, and that should decrease the noise. Okay, so what we did here is we trained people for 7 days on a task that is a simple 2-choice task with confidence ratings. And this is work by my former postdoc, Jiwan Bang. So what did we find? We find that over 7 days, the intensity threshold, which is the threshold needed to achieve a certain level of performance, goes down. So this is just, you know, standard perceptual learning. People get better on the task. If you just look at a certain level of the stimulus, you can compute D prime, and D prime goes up. So again, this is just standard perceptual learning. So you know, as sensory noise decreases, D prime goes up. Correspondingly, confidence goes up. So all of this is just what you would expect. And now the question is, what happens to M ratio, right? So the threshold improved, D prime improved, confidence improved, but our model says that M ratio should go down, and this is actually exactly what we find. So M ratio goes down over the course of the 7 days, just as our model predicted. So the as you have less sensory noise, you have a lower metacognitive efficiency.
How do you measure confidence?
This is just a 4-point scale, 4-point rating, 1 to 4.
I'm sorry, what was the task? Was the same left or right?
Sure. So the task, I didn't include that. So this is the task. It's just a simple 2 IFC, 2 interval force choice task. So stimulus appears in the first interval of 50 milliseconds, then fixation, then the second interval, and then people need to say, is the stimulus, is the Gabor patch in the first or in the second interval? So in one of the intervals always has the Gabor patch, the other interval always has noise. So they give that response, and then they give a confidence rating. But honestly, any task, any 2-choice task should have given the same result. But this is the task that we happen to use.
Excuse me. Suppose you ran that task with that Gabor patch with its angle down in the corner there, and after they were trained, you then started them on a fresh new Gabor patch somewhere else. So it would be a different stimulus, a different location, different angle, different everything, but they would have gotten more confidence just in their own ability and knowing what they're looking for. Would you expect to get this to translate to the second task or to other tasks?
So this is one of the lucky times when I don't need to guess because we have the data.
I was sure you did.
We trained on a particular orientation and in a particular quadrant, but then we also tested different orientation in the same quadrant as well as a different quadrant of space. So we tested for generalizability, and the finding was that we, the finding as in the effects on M ratio. Well, we didn't find learning on those stimuli, so performance didn't improve, but also confidence didn't change and M ratio didn't change. So it wasn't any kind of other stuff that happened. The change in confidence and the change in M ratio was driven by the change in performance. When we tested different stimuli where there was no change in performance, there was also no change in confidence and no change in M ratio.
So is there an assumption that the sensory noise is independent of the metacognitive noise? And does
yes, so that's what we're assuming. It's hard to imagine that it's anything different for us because we think of these as coming from very different levels of the system.
But your generalizability test seems to prove that, doesn't it?
Seems to prove that to the extent to which seems to suggest, I mean, you know, it's data, right? Data doesn't prove anything, but it suggests things. So yes.
Well, it supports it, right? It supports it. I mean, you can test for that independence using that generalizability data. You can look at relations between the noise, right?
Yes. So I guess in a way I've always taken that as a given, but yeah, if you think that's an interesting question, then I guess our data actually already provides pretty strong support for that. Yeah.
Well, since it's an important assumption in this prediction, so the prediction is only counterintuitive when you consider the efficiency. Really, what it just means is the metacognitive noise swamps the sensory noise. So it's not entirely unsurprising that the efficiency should drop, but that's only valid insofar as they're independent sources of noise. And so you could do that. Your generalizability test is a good way. You could also look at individual differences. The individual differences might support the independence of the noise.
We also looked at individual differences. So the people who learned more, so who had larger increase in D prime, they also had the larger decrease in M ratio. So there was a very strong correlation there.
Excuse me, did your 7-day timing hold when you went across different tasks? Did it translate? If people had done 6 tasks in a row and it took a week to get there, did it take a week on a new task that was similar but with some differences? Are they really truly independent? Are they changing their confidence as they become better subjects?
So what we did is on days 1 and 7, we had this additional stimuli, and there was no difference between days 1 and 7 on the other stimuli that we didn't train. We didn't try a separate 7 days for any other task in this study.
Because they may be learning confidence too, and so you would have to that would predict that it would not hope perhaps.
Yeah, so I don't think they're learning confidence because again, for those other stimuli, confidence didn't change and metacognition didn't change.
It seems counterintuitive for my years of doing psychophysics. When we hired professional subjects that would come back over and over, they seem to pick it up faster. They seem to learn the task faster, as though they were getting rid of extraneous noises and they understood the task and they understood what it was like to make a decision and be wrong and that sort of thing. And I got the impression that our professional subjects really shorten the experiments a lot by having professional subjects, but you don't find that, you're saying?
I'm not sure what you mean. So I think our subjects they're doing the task well on day 1 already. They're just getting better over time. I think that's a finding that people get better over time.
Oh, yeah, I understand.
Yeah.
I just wanted to know what exactly you mean when you say noise in the stimuli. So you talk about similarity, but your actual task is not really related to the degrees of orientation or.
Yeah. So that's a great question. There is an assumption here, which is that the metacognitive. Sorry, the assumption is that the learning is making is decreasing the sensory noise. You're getting more consistent over time, and that is the decrease in sensory noise.
But more noise means what exactly in your task?
So in signal detection terms, noise would be lower variance in these distributions.
Yeah, but in your
so that means that this is a between trial distribution. So that means that you're more consistent. The individual trials are more similar to each other later on in the training.
Okay, because for me, the task is actually about the localization of the stimulus and not really related to the stimulus per se, so the orientation of the patch.
So, I mean, you know, the signal detection framework is very abstract. So I think it doesn't really matter whether the task is about orientation, about the location, about you know, the spatial frequency of the stimulus. I think conceptually you'd get the same results. You don't think so?
I mean, I just wanted to know what exactly you mean by stimulus noise, because for me, yeah, it's more related to the similarity between the orientation, for example. So
yeah.
But yeah, maybe just you can go on and maybe if I have some.
Yeah, I mean, so you know, so all of these so a perceptual learning manipulation, you can think of maybe does something else, and I'll be happy to admit that it probably does other things as well. I'm not sure that I have found anything else that perceptual learning can possibly do that would predict that M ratio would go down. In my mind, this is the only explanation that I have seen that, you know, accounts for this finding. So, yeah, maybe we can go back to that at the end. So this was one experiment. We wanted to make sure that, you know, this is something that that is consistent. So we ran a completely different experiment that is again based on the same concept of learning. So we wanted to ask, does the same effect appear on the order of minutes rather than days? So usually the way you know, your data is going to look like this. So you're going to have you're going to have some subjects, and each subject is going to do a bunch of trials. And the way we analyze this data is we look at one subject and we analyze all of these trials, and then we compute D prime, we compute confidence, we compute whatever we want to compute for each subject. So this is what I'm going to call here standard subject-based analysis. I could have just called it analysis. You know, this is what we do. But there's something else we can do, which is pretend that there's not meaningful difference between the subjects, or just look at each trial separately. So analyze all of the trials, all the trial one, you know, trials for each subject, then analyze all trial two, and then get D prime for each trial, get M ratio for each trial. And what we call this is trial-based analysis. So this would allow us to actually see how learning is taking place on a very fast pace. So, you know, from trial 1 to trial 97 in this study, we can see how learning is happening, and we can test for the same predictions on the order of minutes rather than days. So in this study, we used two different tasks. One is what we think of as the detection-based task. So this is a course orientation discrimination task. So the Gabor patch is either 45 degrees or 135 degrees, and it's embedded in a ton of noise. So in this case, it is this orientation, 45 degrees. And again, there's fixation, the stimulus appears, people give a response, and people give confidence. So this one task. The other task is a discrimination-based task, where again, the task is they need to say if it's clockwise or counterclockwise from vertical, except that now we use very high contrast, but we make the orientation just off of the vertical. So the orientation is less than 1 degree tilted from vertical. In this case, it is left tilted, or that is counterclockwise tilted. It's hard to see, but you know, this is what subjects actually saw. And again, we had 178 subjects doing 97 trials each. This was collected on Amazon Mechanical Turk. So what did we find? When we look at the detection-based task, over the course of the 97 trials, we see a D prime increase over time. So people get better, and we can see that over the course of these 97 trials. And correspondingly, M ratio goes down. And it's a really significant increase and really significant decrease. This is the kind of stats you get with 178 subjects. This is for the detection-based task. Interestingly, the discrimination-based task, we see the same effects, but they're much more attenuated. So the learning is much less steep, and correspondingly, the decrease in M ratio is much less steep. So what this tells us is that, you know, the effect in M ratio is really driven by the effect in D prime. And we can compare these things statistically, and it turns out that in the detection-based task, the learning is greater than in the discrimination-based task. And similarly, the decrease in M ratio is steeper in this task compared to this task. So we say see the same effects both with standard perceptual learning as well as this abridged version, but with a lot of subjects.
Question.
Mm-hmm.
To get D prime as a function of trial number, are you pooling across subjects?
I'm pooling across subjects, yeah.
And how confident are you that all the subjects have the same D prime?
I'm absolutely confident that they do not. So it is a different kind of measure than what we're used to. I think that you know, there's always pooling involved in any kind of analysis, right? So when I analyze all of my trials for a given subject, they probably got a little faster over time, but I'm pooling anyway. So here you can again do the pooling, and you just need to live with the fact that you're getting subjects who have a different distribution of ability level, but you know that doesn't, so you know, that makes the data dirty, but it doesn't change the prediction. And we have also done simulations here where, you know, we have simulated subjects with different different levels of D prime, and you know what happens when you pool the data for simulated data like that. And what happens is, if in the presence of M ratio you get these results, in the presence of metacognitive noise, you get the same kind of results. In the absence of metacognitive noise, you know, this still goes up, but M ratio actually stays flat. So according to the simulations, again, this decrease is driven by the metacognitive noise.
Were all of these tasks 2AFC?
They're discrimination tasks. So it's a left-right discrimination. Okay, so we have developed and tested the model. We have made the model make a prediction that is at least not obvious, but regardless of whether you think it's intuitive or not intuitive, none of the other existing models in the literature make that prediction. So clearly, there's something about this metacognitive noise thing that is needed in order to explain the data. And you know, you can use that to make new predictions, and then those predictions turn out in data. Now the question is, can we use this metacognitive noise to now inform our measures of metacognition that we have, and develop a better measure of metacognition? So let me go into the second part of my talk, and I see that it's already been a while, so I'll try to go a little faster. So what do we want in a model, in a measure of metacognition? The most important thing that we want is that it varies with actual metacognitive ability. So as confidence ratings are more informative, it should go up. But importantly, it should not vary with what we call nuisance variables. So it should not depend on the confidence criterion location. So if it does depend on the confidence criterion location, that means that people that have higher confidence would be shown by this measure as having either higher metacognition or lower metacognition, and this is not something that we want. So just your level of confidence, which you can modulate easily, should not be related to the measure of metacognition. The other important nuisance variable is the accuracy on the task. Again, whether you're more accurate on the primary task or less accurate on the primary task should not affect our measure of metacognition. So we can test whether these things are true for the existing measures, and then if they're not true, we can think about what can we do to develop a new measure that for which this would be true. So what we did is first of all, we used the continuous confidence ratings. So confidence was given on a continuous scale from 50 to 100. This is what the rating looked like, but people could give anything in between these numbers. We used 3 different contrast levels. And here we did a more standard psychophysics thing where we had 20 subjects and they each came for 3 sessions and we got a little less than 3,000 trials per subject. And this is work of my graduate student, Meda Shekhar. So what did we find about the existing measures of metacognition? Let's look at M ratio. What we see, so we call it meta d prime divided by d prime. Here is the same thing as M ratio. When we look at M ratio as a function of the confidence criterion location, we see that it decreases continuously. So as you use a higher confidence criterion, you get lower measure of metacognition. On the other hand, there is no difference between the 3 contrast levels. So that's a good thing. We don't want them to be different. And all of these decreases are highly significant. Now, if you look at just meta d prime, what we see is, again, all of these decrease the same way. So these are the p-values. But on top of that, there's also a difference between the different contrasts. So the high contrast value looks like it has, high meta d prime. The intermediate contrast value has intermediate meta d prime, and the low contrast value has low meta d prime. So this is what makes meta d prime dependent on accuracy and thus a worse measure than meta d prime divided by d prime. When you divide, then you at least don't get difference with contrast. So accuracy doesn't matter, but you still get this difference with criterion level. So you have this constant decrease. So in that sense, actually meta d prime divided by d prime, or M ratio, it is not a good measure. It varies with this nuisance variable that it shouldn't vary with. So what do we do? First of all, how do we model this decrease? What is this decrease? Where is this decrease coming from? We can think of our standard signal detection theory model. So this is a situation if you have a 3-point confidence rating. So this is your decision criterion, and then confidence criteria on each side. So this would be high, medium, low level of confidence for S1, low, medium, high level of confidence for S2. And there's no metacognitive noise, no nothing, right? So this is just standard signal detection theory. The model that I was talking to you about would just add Gaussian noise to each of the criteria. But the problem is if it's Gaussian noise, the noise is going to be the same for each criterion, and then we're not going to get this decrease in M ratio for the higher criteria. So what we think is going on, and the way we model it, is with log normal metacognitive noise. So a log normal distribution has this property that as its mean increases, its variance increases. So criteria that are very close to the decision criterion, so they have low mean, they're going to have low variability as well. Criteria that have high mean are going to have high variability. And the same thing on the flip side. So the criteria are now log normally distributed. So we're going to compare these three models. We're going to first fit them to the data. And then we're going to look at how well they fit. We're going to use a Kaike information criterion, or AIC, but really any other measure like BIC and other measures produce the exact same results. And just so that you can interpret these results, AIC difference of larger than 10 indicates substantial support for one model over the other. So this is when we compare the log normal model with the standard segmentation theory. So you can see that there's a whole bunch of subjects for which the log normal model wins very strongly. And there's a few subjects for which there's really not any difference between them. And these are the subjects where metacognitive noise is actually close to zero. So the two models become pretty much the same thing. The log normal metacognitive noise becomes the same as the no metacognitive noise. So overall, the log normal noise model is a lot more likely, 300,000 times more likely than the standard segmentation theory model. We can also compare the log normal metanoise to the Gaussian metanoise, and we see the same results. Now the Gaussian metanoise is better, but it's still about 6,000 times less likely than the log normal metanoise model. So just from these fits, it looks like the log normal metanoise model just does better than these models. But we want to see, this in the data. So again, this is the data that we observed. And this is the predictions of each model. So the standard segmentation theory model predicts that in the absence of metacognitive noise, meta d prime is always going to be equal to d prime. So this is a simulation. So that's why this is not exactly flat, but there's a little bit of noise in here. And same thing for meta d prime. The Gaussian meta noise actually counterintuitively predicts a slight increase with higher confidence criterion locations, which is the opposite of what the data is showing. And it's only the log normal meta noise that shows the same qualitative effects than or compared to the data. So the log normal meta noise seems to be capturing something important about the data here. So finally, the whole point here is to see, can we use this log normal metacognitive noise model and derive a measure of metacognition that is better than the existing ones? So this log normal metacognitive noise has this parameter sigma meta, which is the metacognitive noise, right? It's a parameter of the log normal distribution. So we can look at whether this new parameter can serve as a good measure of metacognition. So this is, first of all, the Gaussian meta noise model. So we see that the parameter, the metacognitive noise parameter for that model doesn't differ between contrasts. So that's good, but it increases for the different criterion locations. So according to this model, there's worse metacognition for higher criteria locations, which is the same thing that we observed for M ratio. So that's not great, but we can look at, and all of these things are, so the effect for confidence criterion is significant, for contrast is not, so that's good, right? So we don't want a difference with contrast. When you look at the log normal meta noise model, now everything is on top of each other, so that's great. It means that our measure of metacognition doesn't vary either with the confidence criterion or with the contrast. And this is frequent statistics here. We have done Bayesian statistics as well, and that's actually positive evidence for the fact that there is no difference between the different contrasts, and positive evidence that there is no difference between different confidence criteria. All of that makes sense? Okay. So what we have done here is now we have developed and tested the model, and from that model we have derived a new measure of metacognition that for the first time has all of the properties that we wanted to have. We wanted to be independent of all of these nuisance variables. And importantly, there's a clear connection between the measure and the model. The measure is derived from the model. We know how those two things connect. Previously, all of the measures that we have, they do not have corresponding models. All of the models that we had, they did not have corresponding measures. Now, the third part is I want to link this to brain function, and this is going to take about, let's say, 6 or 7 minutes. We're already quite a bit into our time slot, so I want to leave it up to you. Do you want to hear about this in the next 6 or 7 minutes, or do you want to stop here? I don't know who's the decision maker.
Let's
I
hear
see
about
some nods, but I only see a few people.
Yeah, keep going.
Yeah, let's hear about it.
Let's hear
Okay.
about it.
Okay. All right. So let's link the model to the neuromechanisms. So just as a very brief introduction to the literature on metacognition, to the neuro literature on metacognition, we know that there's two regions, DOPFC and APFC, which are particularly important. There's a number of findings where DOPFC tracks the confidence levels. So high versus low confidence affects the activity in DOPFC, versus APFC has been linked specifically to metacognitive ability. So people who have higher metacognitive ability have higher volume in gray matter volume in APFC compared to people who have lower metacognitive ability. So how do we connect these findings to our model? So this is the model that we have. I've taken away the stimulus level. So we have the decision and the meta level. And here we have a picture of the brain with DOPFC and APFC, and this idea that sensory signal is somewhere in the back of the brain, and it needs to go to these areas in order for for confidence ratings to be given. So connecting these two would suggest that there's a specific model that we can postulate, and this is a neural model now, where DOPFC reads out the sensory signal and relates it to APFC, and APFC makes the final confidence judgment. Now, obviously, this is a very simplified, I would say oversimplified picture, but we think that it captures something about what is going on underneath. So let me put the same model in a different way. So we have the raw sensory signal, it goes to DOPFC. Then the DOPFC sends the sensory signal strength for confidence to APFC, and APFC makes the confidence judgment. So how do we test this? What we thought about is we can use TMS, transcranial magnetic stimulation, in order to disturb each of these regions and then make different predictions for these two areas. So if we TMS DOPFC, what we should see is a change in just the level of confidence. So people should either have higher or lower confidence, but not a difference in metacognitive ability. So if DOPFC just extracts the sensory signal and you TMS that, there should be less sensory signal, so confidence should go down, but the quality of the judgment should not change. Versus if APFC is TMS'd, then we should not see a confidence change, we should see a metacognitive change. So the quality of the metacognitive decision should be different, but the level of confidence should not be different. So this is our paradigm. People fixated for 500 milliseconds, then a stimulus was presented for 100 milliseconds, and then the response took about a second on average. Now, within this paradigm, we needed to figure out when to actually TMS the brain. So we think that the confidence computation happens right about this period. We don't know exactly when it happens. And that's why we sent 3 TMS pulses and at 250, 350, and 450 milliseconds after the stimulus onset in order to cover this time period when we think that the confidence computation is happening. And what we did is we TMS'd APFC, DOPFC, and S1 separately. And S1 is just the primary somatosensory cortex, which we used as a control site. So what did we find? When we look at just the confidence level, this is S1 or our control. Question? Okay. So when we look at just S1, this is our baseline. And as you can see, TMSing APFC doesn't change anything, but doesn't change the confidence level, but TMSing DOPFC decreases the confidence. So TMS to DOPFC selectively decreases confidence, versus when we look at metacognition, now TMSing APFC changes metacognition, but TMSing DOPFC makes no difference. So you see this dissociation between TMS to DOPFC versus TMS to APFC. And now importantly, we can go back to our model and we can build a computational model to explain these findings. In the computational model, TMS to DOPFC would decrease the readout strength. So we're going to model that as the readout is decreased by a certain amount, versus APFC, TMS is going to change the metacognitive noise. So we're going to decrease the metacognitive noise by a certain amount. And these are the data that we got, that I showed you. And this is the results of the model simulations. And as you can see, the same pattern of results emerge in the data and in the model. So as conclusions, we developed a model of metacognition that makes new predictions and explains data that were not explainable before. And this is the log normal meta-noise model. And the critical thing here is 2 things. One is there is such a thing as metacognitive noise, which affects the confidence ratings, but not the decision criterion. And the second thing is the confidence criteria that are further away from the decision criteria are noisier. And that's captured by this log normal distribution. We link that to our ability to measure. So that model suggested a measure of metacognition that turns out has much better properties. It doesn't vary with the Nuisance variables of confidence and accuracy. And it can also be linked to the function of different brain areas. So we think that we have some good evidence that DOPFC does something that resembles reading out the sensory signal, then passing it to APFC, which does the computation for confidence. So that's it. Thank you for your attention. And I want to thank my lab members, my collaborators, and funding sources.
Hey, Bill, you're going to unmute yourself?
Sorry. My question is, Ms. Ken, the first finding is, it's very simple. You know, you have the 2 variances of standard deviations under the square root sign. And the model seemed to make a very clear prediction. Could you, I mean, you may not want to do this, but can you just state the model and the causal properties just in some English sentences? If you had to tell your grandmother about this.
Sure. Well, if I need to tell my grandmother, then it may be.
Or maybe your grandmother's too smart, but somebody who doesn't know about math.
So this is the model, but if I'm just to say it in English, I would say that the stimulus is first corrupted by sensory noise. I guess these are already terms that are difficult to process, but I think the people in this call can process these terms easily. So the stimulus is corrupted by sensory noise, and you make a decision based on this internal representation that has sensory noise. But when you make confidence ratings, or when you make confidence judgments, there is an additional level of noise that is not present when you make the perceptual decision. This is really the essence of this model.
So if you put in traditional things that kind of affect those criteria, such as payoff ratios, you tell the people in Oahu expect an attack, and they see things better on the radar. Is that the kind of noise you're just talking about? How about that? Just people know when they haven't got good information, and they feel better about it, because it seems to me there's a piece of people feeling and happiness that you're putting in your confidence too. The belief that they're making the right decision. It's a very psychological model, but there are ways to push things like that around, and have forever been, such as John Switz did experiments where he asked people to make a second judgment. In case the first one is wrong, make a second judgment. And people can do that and can do pretty well on it. Mm-hmm. So this is really a psychological model, isn't it? If there's an additional noise, a psychological noise, I'm thinking about what Ken said.
So I'm not sure what psychological model means. It's a cognitive model in the sense that we postulate some noise. I have been thinking very, very seriously about where this noise comes from. So we're just submitting a paper where we are proposing that there's 5 different sources of noise. And these different sources can vary in different ways. They can be signal noises, they can be computation noises, they can be systematic or non-systematic. So there's many ways this noise, there's many sources of this metacognitive noise. But for our purposes, it doesn't matter exactly where it comes from. And as you said, people can be pushed to have higher confidence or low confidence. That's fine. This is not metacognitive noise by itself. So if I just make a do some manipulation, or just ask you, please give higher confidence, and you just shift your criteria in one direction, but they don't get noisier or less noisy, if the noise level stays the same, your confidence level is going to shift, but your metacognitive ability, which is how well the confidence predicts the accuracy, is not going to change.
Even with attention, if you tell somebody they're gambling for dimes or hundreds of dollars, you don't get some differences in the variation that they don't.
So people have done experiments with attention, and the finding is that D prime changes, but M ratio doesn't change. So it's actually very difficult to affect metacognitive ability. People have done dual tasks that is supposed to actually tax cognitive control, right? It's supposed to tax the same regions, DOPFC and APFC that I've been talking about. And the findings are mixed. So some papers find a decrease and some papers find no change. But that's a very different kind of manipulation.
I have a question. Several years ago, I had some discussions with Stephen Fleming on metacognition. We had some arguments about that. Is your approach to metacognition different from Fleming's?
I think we have similar approaches. I think, the details of the models that we have proposed are different. As in, he has proposed some models that are not this. And obviously we're proposing these models, and, they seem to work well for different things. But how he and I think about metacognition, I think is very similar.
The TMS, it decreased metacognitive noise?
Yeah, so that's a great question. We did not expect that.
Yeah,
we
that's very
definitely expected that metacognitive noise would be increased by TMS, but this is also something that this was actually the third time we or somebody else finds that TMS to APFC improves metacognition. So this was an online study. Previously, we had done a data burst TMS, so that's offline, and we saw an increase as well. And the same thing was seen in a memory task. So, you know, it is in the opposite direction of what you would expect, but it is consistent. So
that result was very surprising, much more counterintuitive and surprising than the other results. And so the question is, first, what else can you do to reduce metacognitive noise? What behaviorally can you do? So perceptual learning didn't, but what else can you do to improve it? There should be some way to improve it. The second question is, why does the brain not just do that automatically? And the third question is, does metacognitive noise actually serve a beneficial purpose? Is it adaptive? Is it a good thing? And when you're TMSing, you're improving metacognition or metacognitive sensitivity and reducing the noise, but that's actually somehow a bad thing. So is metacognitive noise a good thing for some reason?
So these are great questions. I do not have great answers to any of them, but I have told some funding agencies that I'm gonna investigate these things, and they were happy about this, so they gave me money to do that. So what I can tell you is, you know, what I think and, you know, what I would speculate. And what I would speculate is that there's a number of different reasons why we have metacognitive noise. One is, you know, it's just difficult to keep the same criterion, right? So it's just limitations of the system. So if I change my criterion from trial to trial, even if, you know, that just metacognitive noise, right? So I don't want to do that, but it's difficult not to. So that's one potential reason. Another potential reason is I am changing my confidence on purpose, right? So maybe you, maybe I was confident on the previous trial, and now I'm more confident on the current trial. This is bad, this is metacognitive noise, but maybe in the real world is actually a good thing, right? Maybe I'm using some other cues, like I'm using my reaction time as a cue. Maybe I'm using my arousal level as a cue. There's papers on both of these things that people are actually using these things as cues when giving confidence ratings. Again, this is a bad thing in my psychophysics task, so it is metacognitive noise there. Maybe in the real world is not a bad thing. So these things suggest different interventions for decreasing metacognitive noise. If I want to just decrease metacognitive, you know, if I want to improve your ability to be consistent, then maybe just a lot of training over time, maybe more instructions, something like that would help. We have actually done some of that. It doesn't really work. But if it's something that you're doing that you can change, if we can tell you, you know, you have this autocorrelation in confidence, you are using your arousal in this way, and try to be mindful of that and not do it, maybe some of that would work, and maybe we can improve confidence ratings in that way.
What about borrowing from the equivalent noise literature, where noise thresholds are thought to establish perceptual stability or continuity, so that we don't, in other words, if you have a contrast versus threshold function, you have a dipper-like function, setting a threshold allows you to perceive things as being stable or sharp. Blurry edges don't appear to be blurry, they appear to be sharp because we set a threshold. We did the same thing for metacognition. What it would result in is the feeling of stability in our confidence ratings. We would think we were making the same kind of confidence from moment to moment, as opposed to the alternative, which is maximizing metacognition sensitivity. If we maximize it, that means from moment to moment, we'll have a lot of uncertainty in how confident we are. We'll feel those fluctuations.
Mm-hmm. That is very interesting. I would need to think more about this. I would,
So the idea would be to look for a Dipper function in metacognitive judgments.
So do you think that the Dipper functions that exist, that are known in psychophysics, do you think the same manipulations would lead to Dipper functions in metacognitive judgments, or?
That would be the fascinating, yeah, that's the question. If that happened, it would be fascinating, because it means the brain is inserting the same sort of thresholding process wherever there's, at whatever stage you have, whether it's 2 stages or 5 stages, at whatever stage you insert a threshold in order to generate, stability or a feeling, or the appearance of sharpness or the appearance of stability in the world.
Mm-hmm.
Anyway,
that is super interesting. I'm going to follow up with you actually to ask for some of those papers that you have in mind, and we can easily try some of these things with confidence ratings.
Cool.
And yeah.
Can I ask a silly question, I guess? If you reinforce people in a task on every single trial, told them they were correct, and part of the time you lied, my guess is their performance is going to go down. And if it went down, would you say that's metacognition, or that's the thresholds that they're holding for stimulus response, stimulus judgment?
Yeah, so that's a good question. So the way I use metacognition here is just as it's something that happens on a single trial, and that's it. Now, obviously, metacognition has the important purpose that once you know what happened on this trial, then you can change your strategy for following trials. And I think this is the kind of thing that you are alluding to. So if you give wrong feedback, for example, what is going to happen on the following trials? Would the decision criterion change? Would the confidence ratings change? I know a little. So I know of a couple of studies that gave wrong feedback or corrupted feedback. They didn't include confidence ratings though. So they did see a decrease in D prime.
Sure.
Which,
But would you say that's because of they're changing confidence ratings, or they're causing how well they keep a perceptual threshold? Correct? I'm just trying to get a grasp on what the confidence ratings really get. This second process.
Yeah, I mean, I think the reason why you're making any kind of adjustments over time is a metacognitive process. But that's a different level of metacognition that I have presented in this talk. But yeah, I think it is a metacognitive process. So if you are changing your decision level mechanism, you're using, what is, in my mind, just by definition, a metacognitive process.
In a sense, it's like making them more inclusive, making more inclusive of possibilities. This is a way of like saying you've added another noise.
Sure.
Mm-hmm.
Well, that question suggested something else. I was wondering if you were to give subjects incorrect feedback, but only when they're correct, would that make them less confident? Or if you gave them incorrect feedback only when they're wrong, you tell them they're right when they're really wrong, would they become more confident?
Yeah. So essentially what you would be doing is you're telling them that they're either more correct or less correct than what they really are. We know that people are pretty sensitive to this kind of feedback, so they can move their confidence in the direction of the feedback. So if I tell you you're correct on every trial, even if you're not very confident, you're going to get more confident over time because you don't think you're getting it right every time, but I'm telling you you're getting it every time, correct every time. So, you're going to get more confident over time. Now, the question is what happens to metacognitive ability? And I think that probably not much is going to happen, in the sense that you're making people give higher or lower confidence ratings, but you're not improving or making their metacognition. You're not improving their metacognition, you're not making it worse. You're just pushing around the criteria in a up or down. Now, of course, it's an empirical question. There may be something more that is happening, but that would be my prediction.
Hi, Dobie. I also have a question. This is really cool research. And I actually have a question about the first part of your presentation, so very early on, when you presented the finding published in JPG. So I was kind of wondering, because basically you're saying that you found this decreasing sensory noises and how it's correlated with the decrease the metacognitive, sorry, I forgot the word. So the racial, the M racial. So I was kind of wondering, yeah. So, I mean, I am convinced that this is definitely a supporting evidence for your model, but I was kind of hesitating to believe this is sufficient to say your model is true. So it's kind of like necessary condition, but not sufficient. So I was kind of wondering, do you have more evidence to support your initial model besides this one? Is there anyone, or can you tell us how this evidence is, because you mentioned like other models, other competing models cannot fit in this result. So I was kind of wondering how exclusive this result could be necessary.
Yeah. So it's a great question. What I would say is, I do not think that this model is literally true, in the sense that much more is definitely happening, right? So this is a huge simplification. As I was saying, I think that there's at least 5 sources of metacognition, right? And there's one term here which is called metacognitive noise. And the thing is, you know, in a 2-choice task, there is no manipulations, no nothing. I think that actually does a decent job at capturing all of those different sources. But it's not the ultimate model of metacognition. It's missing a lot of things. So in that sense, to me, it's even meaningless to say it is the correct model. It's not the correct model, no. Maybe it's meaningful, and then the answer is no, it's not the correct model. It is a model that is a big simplification, but it's has just enough amount of detail to make an interesting prediction, or at least a prediction that is not made by other models. But yeah, I agree. I have not proved that this model is correct. I have only showed that one prediction it makes, you know, is supported by data.
No, but it's still meaningful. I just kind of curious because I'm not familiar with other models, so I was just kind of wondering. Yeah. Thank you so much.
Okay, well, I got my sound turned on. We usually end with an attempt at simultaneous clap, and I always start it and everybody claps a second after I do. So 1, 2, 3. Christina,
We're
you're
getting better at this.
Thank you very much.
Thank you so much. This was really fun and very lively group. I really enjoyed it.
Thank you very much. It was great to see you. Wonderful talk.
Thank you.
Thank you, guys.